I'm a software engineer for Huawei Allen Research Center. And today, over the past 3 years, I worked closely with our SRE teams to ensure the reliability of Huawei cloud services from the design phase. So today I'm going to talk about blast radius reduction for large-scale distributed systems, so mostly from design phase, design perspective. So we all know that building large-scale distributed system is hard because it's high complexity. This diagram it shows the high-level architecture for typical global services. So, as Charles Perrow argues in his book Accidents, that system complexity makes failures inevitable. But why? From my point of view, there are primarily three reasons. The first one would be the black swan. Of course, the bad ones, we could be good in black swan, but we are talking about black ones, usually out of control and hard to predict with severe consequences. For example, natural disasters or even some construction work cut off your networking cable. That's what happens. And the other one would be blind spots. So it's kind of system error of human beings. And that's why we need collective work, teamwork to minimize the blind spots, like code review, design review. The last one would be trade-offs. We are always making trade-offs in our software design. No matter it's because this business purpose versus cost versus profit, or technical trade-offs such as the CAP theorem. The relative cost to building a perfect system is similar to the relative mass of an object when its speed approach and the net speed. So that's why we have to design for failure. But today we're looking from mostly from the blast radius reduction angle. The definitions of blast radius may is domain specific, depends on what kind of your service. But for our cloud services, usually depends on it's determined by the impacts of the customer impacts, resources, or any other workload in case of failures. So based on experience, we recommend blast radius reduction should be part of your system design. And then it should be one of the reliability metrics when you're evaluating the reliability of your system. For example, based on the failure mode, we not just focus on how you deal with the failure mode. We also think about what if you didn't recover from the different failure mode. That's why we need isolation to reduce the blast radius. Which makes isolation crucial, is essential, not optional for building highly reliable cloud services or large-scale distributed systems. So, but when we determine the first trade-off we have to make is between the blast radius versus the elasticity or cost. The one extreme would be the standard mode, which is easier to implement maybe, but is very hard to maintain, as impossible for multiple tenancy systems. And the other one would be going for tenancy that you have for all customers sharing the same resource pool, but the blast radius would be too large. So we have to make a balance. It's kind of art. There's no golden rule how to make the balance. It depends on the service, depends on what kind of things you have to value. And from the architecture perspective, usually we have layered architectures from infrastructure to the virtual resources to high-level applications. But usually the strategy would be the lower the services. Usually we prefer simple complexity, and high-level applications we could have more complex strategies to do the isolation. But here are just a few examples. But today I'm going to focus on the cell-based architecture. So if you're not quite familiar with what is cell-based architecture, there's a good reference from AWS re:Invent. You could watch the video on YouTube. So in short, cell-based architecture is basically kind of split your large cluster into fine-grained smaller clusters, usually with even 100 or more, depends on how the granularity you want to, how much the blast radius you want to contain. achieved. Basically, one cell is the smallest cell-contained scale unit. So one cell could be a single cluster serving customers. That means when you scale your cluster, is basically adding more cells. So the key benefits of cell-based architecture is the predictable blast radius, predictable performance, predictable scalability, and there are many more other benefits. So here, the diagram you could see this is a kind of classical cell-based architecture pattern. You could have you have different cells processing the request or workload for different customers. You need there's a called cell router layer to routing or dispatching the traffic to different cells. This is the ideal situation, but in practice, maybe it's more complicated, especially for stateful applications. So that's the data synchronization would be the most challenging part to deal with. That's why in practice we may have to focus on the stateless layer. So usually for complex services, you may have multiple layers. So stateless layer is the most straightforward a layer to implement cell-based architecture and offload the complexity of data synchronization to a storage layer. It may depend on some dedicated database, for example, Google Spanner, DynamoDB, or Cosmos DB, which provides some global synchronization, cross-AZ data synchronization capabilities. And this will be simplify your implementation. So for other than depends on the top layer cell router to do the traffic dispatching, which add additional complexity. In practice, you may also depend on what kind of service you have. For example, for DNS service, for load balancers, for load balancer itself. So usually the cell router is implemented based on load balancer. But how could you do cell-based architecture for load balancer itself? So in that case, we're not able to have another layer on top of the all the cells. So our approach would be to have a control plane which do kind of called cell controller or any other managers. They have predefined talents to cell mapping. So for example, for DNS, you could, based on name servers, different customer, you assign different name servers for each cell. Or based on load balancers, you could have, when customer create load balancer, based on your strategy, you could assign to different cells and to basically advertise your virtual IP, the customer virtual IP for each cell, different cells. How about the high availability for each cells? You may don't want just have one cell for one data partition. So in practice, you may have multiple locations. Locations here could be AZ, data center, or even geo locations or region. So what we do is we have, based on the data partition, we have different cells across different regions or different AZ. And so this is a high-level diagram, what we do. So basically, if one of the cells fails in one location, the other take over. But how one single cell looks like. The first diagram is the more ideal, but in practice it's more complex or messy. So you may have to, if you have a lot of microservices for your architecture, you may not include or include all of them in one cell. It highly depends on what's your critical path. So ideally, all those key microservices should be included in a single cell, so they don't have dependency of across different cells. It maybe causes more complicated cascading failures, for example. So this is a high-level example how a single cell looks like. Usually, you may have a microservices as the front end. And then you have many other microservices interacting or dependency between them. So that's for single cell. But how about the challenge and cost? So it's not free to adopt a cell-based architecture. There are probably three costs you may have to consider. For example, the infrastructure. If you want to split your one cluster into 100 cells, it may cost more infrastructures. You cannot equally split 100 gigabytes of cache into just 1 gigabyte per cell. In practice, you may need 5 gigabytes per cell or more. And system capacity, especially if you didn't do it right away, it may cost a small capacity to your system. For example, if you want to do you need to migrate customers from one step to another? It depends on your requirements, but it may make the system more complex. Another would be the operation cost. So if you manage one cluster would be much simple, but if you have 100 small clusters, it would be more complicated to do deployment, monitoring, and so on. So our solution would be to leverage everything as code, not just infrastructure as code. We do many configuration, monitoring, all those things, and try to be then described in code, and then do automation to make the automated deployments, configuration like this. And definitely, it's not service architecture. It's not for small-scale systems. So we talk about is mostly for a kind of spatial isolation, but how about the temporal blast radius? This is basically what we're talking about when an incident happened, how fast you recover. It lasted 1 hour or 1 minute. There's a big difference, of course. So in practice, I think the MTTR, mean time to do recovery, may not quite useful. For example, you do just kind of average. So maximum time to recover would make more sense or more useful. That's more critical, especially for cloud services. There are two strategies. One we call self-healing. Self-healing is basically the fully automated recovery, detecting recovery. So when, for example, this is usually good for kind of predictable failures or great failures. For example, your virtual machine, there's some failure virtual machine, or even you know the health state of your infrastructures, like physical machine, and then you could do some proactive migration. This is for automated self-healing. But fast recovery may automated or semi-automated with some high-level solutions. Is for just like once there's something happened, you could switch to another region. This is what we do. So especially for global services. Another of my work over the past 3 years was building load balancers. We built a DNS-based global server load balancer. We also have level 4 load balancer and level 7. So basically, the global load balancing in our context is not a single service. It's a multi-layer for full-stack load balancing solution. So from the global traffic steering perspective, there are primarily two approaches to implement. As mentioned, I worked on the DNS-based global server load balancing, which is based on the health checking of each region or location. Do switch over automatically or manually by updating the DNS record or dynamically resolve based on the customer request. So there's problems with DNS-based approach. So the TTL of DNS record is one of the reasons. Even some ISP, they don't even respect your TTL, which makes things worse. So that's why we're also thinking about the BGP-based and BGP and cluster-based solutions. So this would be a more reliable approach, but it also comes with complexity, for example, BGP flapping. So other than what blast radius, there's some research called Lamport exposure. So this is a new concept. So basically, other than looking from blast radius perspective, they're looking from the other way, from the client's perspective. So basically, your customers your service did not expose or should not expose the local activity to distant or remote venues. This is basically looking a different way. If you're interested, you could look at original paper. And last thing I want to talk about is the formally verified reliability. So of course, the conventional software engineering practice is really essential and it works for most cases, but we have we still have some incidents happens. So we need a better, which we're trying to explore in a better approach. For example, formal method to verify the reliability rigorously and exhaustively. So based on the formal specification, and model checking and theorem proving. Here is just a few examples of formal language and SMT solver. Yeah, and that's for today. Thank you.